Okay, so today we're doing probability of a single event, just one thing happening. Eventually, Monday next week, we will do the probability of multiple events happening. So that's, it's nice to do those in 2 separate days. Again, I've done it before where I put them all on the same day when we had block periods, and it's a little bit much to do all in one day, but separate, I think you guys will be okay. So there are 2 separate types of probability to talk about. There's experimental probability and theoretical probability. So before I even tell you what they are, I will say the best part about this is most of the time you don't actually need to know which one is which, because if I tell you an example, you kind of know by the example what it is. So if I say, what's the probability that if I roll a dice, I roll a 3? Well, that's 1 in 6. We talked about that earlier. That's actually theoretical probability. I don't really have to tell you because it's kind of obvious by that example. Or if I say, I am shooting free throws, and out of the last 20 shots, I made 12. That's actually experimental probability. But again, you guys can all do that because it's the same stuff you guys have done in the past. So for the most part, it kind of all depends. For the most part, I guess I should say, if I don't specify which one to use, it's usually the one that's painfully obvious. Like, I'm not going to say, I roll a dice, what's the probability I get a 2? What's the experimental probability? That doesn't actually give you enough information, and it's really not ideal to do that. So, long story short, if I don't tell you specifically which one to use, it should be very obvious by the question. If not, I will make sure I tell you specifically which one to use, and I'll make sure I give you enough information. We'll talk about that in a second. Experimental probability is, it's called experimental probability because you actually run an experiment. So these are the ones where if you hear about a probability where it's like, what's the probability that people stop at a 4-way stop compared to slow down and do a rolling stop? That's not like something you can just roll a dice and look at the outcomes. You actually have to have someone that sits down, and every time a car comes, if they stop, they put a check. If they don't stop, they put a check somewhere else. They do that with 400 cars, and then these are their results. One thing I don't think we'll have time to really get into, we'll probably talk about it a little bit, but with those, the more experiments you can do, the better. So that's one of the things that always bothers me when you hear, and you'll hear this with coming political season, they'll tell you, well, actually, 45% of people like this. And it's always a question. They never tell you how many people they surveyed. Because if I see 3 people in the hallway and I'm like, hey, do you play football? And they all say yes, that doesn't mean everybody at Fairfield plays football. So you need the more people you ask, the better with experimental stuff. That's not necessarily here nor there, but fun fact, I guess. Theoretical probability is where you don't do an experiment, you just try to see what you expect to happen. So this is like rolling a dice or flipping a coin, where you know if you have a coin, there's 2 sides. One side is heads, one side is tails. So you can mathematically figure you got a 50-50 shot of getting heads. You got a 50% chance of getting heads. So that's the difference. Again, we'll get a little bit more into it as we go. I think you'll see the difference. But at the very end, and there will be a question on the test that's like this. Yeah, I got 2 examples where it asks you to do both, the experimental probability and the theoretical probability. That's where it's going to be very, very apparent what the differences are. So if you don't understand the differences yet, don't worry. Once we get to that last page, it'll be a lot more obvious. So probability, this is the same thing we talk about. For me, I always put it's once over the total. Some people say it's the number of successful outcomes over the total. And again, we're kind of shifting gears. We're not doing the number of outcomes anymore. We're doing the probability now. Now, we could use the stuff we learned before yesterday and some of the Monday that we found how many different outcomes there were. We could use that to find how many outcomes we want and how many outcomes are total. But ultimately, we want it as a probability today. Okay, so let's get started with experimental probability. And again, if you look at all these examples, you see that they're actually doing an experiment. They're actually doing something X amount of times, and this is their results. A baseball player got a hit in 12 of his last 40 at-bats. What's the probability he will get a hit at his next at-bat? So the probability, this is what I'm talking about, where obviously it's experimental probability because there is no way you can find a theoretical probability of this. And again, also, you don't even have to think about that because I think it's probably pretty obvious. He hit the ball. What do you want? He wants to hit the ball, so that's 12. What's the total? 40. That's how you find your probability. Now, again, remember what we talked about earlier. When you have your probability, you can use a fraction, a decimal, or percentage. Just make sure, if it's fraction, make sure you reduce. So I don't like to reduce, so I usually use my calculator for that. So that is 3 out of 10. If you decimal, that's 0.3, or that is 30%. I don't care which one you use. It literally makes no difference. Always easy. The next one, not to stick with the baseball theme, a pitcher struck out 8 of the last 32 batters that he faced. What's the probability that he will strike out the next batter he faces? So he struck out, or what do we want? We want how many people he struck out of the total 32 batters. So 8 out of 32, again, we can make that into a fraction. That's 1/4. Divide both by 8, which is also 0.25, which is also 25%. I do not care which way you put that. I guess I will say the main thing I do care about is some people put it as a decimal and a percentage. So they say it's 0.25%. That's completely wrong. If it's 0.25, you're absolutely right. If it's 20%, that's absolutely right. But 0.25% is a small percentage. It's not the same. So this is one that could be a little bit more confusing. But again, if it is a little bit more confusing, I guess I should say I do specify. A student rolled a 6-sided number cube 60 times. She rolled the number 4 9 times. So this is also confusing because there's a lot of numbers. She rolled the 4 9 times is what you're looking for. What is the experimental probability that she rolled a 4? Now, this is the one, again, I have to specify. Some of them, the other ones I didn't have to. Number 1 and number 2, I didn't have to specify that they were experimental probability. This one I do because we're talking about a dice. So the experimental probability, again, look at the experiments. You rolled a 4 9 times out of the last 60. That's how you find your percentage or your probability. So 9 out of 60. Again, you can reduce that fraction. I'm terrible at reducing fractions. I guess I divide both by 3. Which is 0.15, which is 15%. This a little bit later, but that's a good example. That's the experimental probability because they didn't actually did the experiment. Whereas theoretical probability would be 1/6. If you roll a dice, there's 6 sides. There's one side that's a 4, so it would be 1/6. Which, fun fact, would be 17%. So pretty close. But that's the difference between experimental and theoretical probability. And like I said, for the most part, I think there's going to be one question on the quiz and probably 1 or 2 questions on the test where you have to make sure you know the difference. Other than that, it pretty much is, I think it's pretty clear by the question which way you're going to actually do it. Other things today, 15 are pickup trucks. What is the experimental probability that Mr. Wise's vehicle is a pickup truck? Mr. Wise. Saw with him for 1 year at Goshen. He's a character, for sure. So there are 2 vehicles total. What do we want? We want one of them to be a pickup truck, so 15 out of 60. Again, I personally, this is where like I said, I'm not good at reducing fractions, or I just am not confident. So I usually make it as a decimal because I just put in my calculator. But again, it doesn't make any difference. This ends up being 1/4. 0.25, which is 25%. Either one of those is fine. I could not care less. Now, again, so far I want to stress, don't get worked up over knowing the difference between experimental probability and theoretical probability, because for the most part, it's very obvious by the question they ask you. Even in number 3, I told you it was experimental probability, and you could find theoretical probability, but given what you just read, I think most of you guys would have put 9/60 and done it that way. So even that one, that is the only one that could maybe be interpreted differently. I think most of you guys would have done it that way anyways with the information they give you. So now these are theoretical probability questions where, again, you don't actually do any trials. You can just look at the numbers and you can look at the math. So your classmate rolls a fair number cube. What is the theoretical, which obviously is a dice, a cube, it has 6 sides. So if you ever see that, what's the theoretical probability? So you roll a number greater than 4. Now, first off, make sure you remember greater than 4 does not include 4. So the numbers greater than 4 are 5 and 6. There are 2 numbers greater than 4 out of the 6 total. So that is 1 over 3. Thing as 0.33. Thing is 33%. Now again, probability, but even if I took out that word theoretical, that's the only way you can do this problem. Because again, the experimental way would be actually sitting there and rolling a dice 45 times or 50 times or 60 times and looking at your results, doing the experiment. Shaw rolls a pair of fair number cubes, so a pair of dice. What's the theoretical probability that the sum will be of 3? And again, we did this the other day, but the way I personally do this is I just think about what numbers add up to be 3. So I start with 1, so you can roll 1 and a 2. And I go to 2, you can roll a 2 and a 1. Then I go to 3, you cannot roll a 3 and a 0. That doesn't make sense. So those are the only 2 options. Those are the only 2 that add up to be 3. So there's 2 that add up to be 3. Out of the total, remember the total options, if you roll a pair of dice, is 36. Remember, we talked about that with the principle. On the first dice, 6 on the second dice, so you multiply those together, you get 36 different options. So 2 of 36 is 1 over 18. Which is the same thing as 0.0555, which I would round to 0.06, which is the same thing as 6%, not 60. Make sure it's 6%. Per usual, I would love to make you guys all round correctly. It makes me a little sad that there are a lot of people, or the amount of people that don't round correctly. But again, at a certain point, I'm not going to worry too much about that because that is not an algebra standard. And when I do worry about that, it makes me depressed. But try to round to 2 decimal places. The last type of problem is, again, one you guys have maybe done before. I talk about how many markers are in this box. So we have 24 green, 16 red, and 10 blue. Find the theoretical probability of pulling at random A, and over here, this notation where it says P and there it says red, that's the probability of choosing red. So that's not a permutation like we did yesterday. If it was permutation, you'd have a number in front and behind it. If it's just P and then has parentheses, that's saying what's the probability of red, what's the probability of green or blue, what's the probability of not green. So the first thing you need to do, unless they tell you this, before I even look at any of those options A, B, and C, I literally will find the total amount because you have to know the total amount. That's what goes in the denominator. So 24 green plus 16 red plus 10 blue adds up to 50. So there are 50 total markers in this box. That's going to go for all these. Again, the denominator for these probability questions is the total amount. Total. Probability that if I pick a marker out at random that it is a red marker. Well, again, what do you want? A red marker. There's 16 of those. Red marker, there are 16 of those out of the total. And again, from here, you can do whichever way you want, a decimal or a fraction. Ends up being 8 over 25, which is the same thing as 0.32, which is 32%. Again, I do not care which one you use, whatever's easiest. Again, personally for me, I'm lazy, so I usually use I can use my calculator instead of reducing a fraction. But that's just me. Now the next one, the probability of green or blue. Now there are some different theories and there's some different ways to do math with this that are a little bit more complicated that we could get into later. We will not have time for that. So for me, green or blue, well, what's the numbers? How many are green or blue? Well, we have 24 green. We have 10 blue, so how many green or blue? It's got to be 34. There's 24 green, there's 10 blue, so if it's green or blue, that's got to be 34. Still over the total of 50, so 34 over 50. That ends up being 17, over 25, which is 0.68, which is 68%. Now, one thing I encourage you guys to do is to double check your work. And when I say, obviously, check your numbers and look at all the little details. But ultimately, just reflect and see if that makes sense. 68% is more than 50%. So that means you have a pretty good chance. Well, does that make sense? Well, yeah, if we have 24 green and 10 blue, that means over half the markers are green or blue. So yes, the probability is going to be higher than 50%. So it's not a bad idea just to look at that with some logic, just to double check things that way. Now, last one, what's the probability that you draw a marker that is not green? Two different ways to do this. The first way, I'm just going to show you, it might take a little bit longer, but I think it makes more sense. So if it's not green, that means your options are red or blue. So you literally do the same way you did B, except for instead of green or blue, you do red or blue. So the red ones, we have 16. The blue ones, we have 10. So that is 26 over the total of 50. So 26 over 50 is 13 over 25. That is 0.52, which is 52%. That's one way to do it. Personally, that's what I would recommend. The other way to do it, and the only reason I'm saying this is so some of you guys maybe will remember it once you get on to like you do more stuff with probabilities. Remember, the probability of drawing all the markers, the probability, like the perfect probability is 100%, or 1.00. So the other way to do it is you could actually find the probability of finding green, and then take 1, which is 100%, 1.00, minus that probability of green. That's a little bit more complicated. There are times that that is easier. If I gave you an example, 3 colors, like green, red, blue, orange, yellow, pink, purple, lavender, I give you a lot of those. It'd be a little bit away. I'm really going to worry about it, but again, that makes sense. If you want to think about it that way, but I don't want to, again, I don't want to dig into it to get people confused. So far, so good. Again, so far, I could have taught this whole lesson and never even really talked about experimental probability versus theoretical probability, and all of these would be doable. You guys could do all these, and it wouldn't be really left in the dark where you didn't know which one to use. So that's what I'm talking about, where ultimately today, I think the hardest part ends up being knowing the difference between experimental and theoretical, but really you don't need to use that for most of the questions on your quiz or on your test. There's only going to be 1 or 2 that you have to know like that. The 1 or 2 you have to know are ones like number 8. And this is one of those that these problems, I get it, but for me, I decided to ask questions when I thought about it. This is one where I can actually make sure you know the difference between experimental and theoretical. So I give you this scenario. I flipped a coin 20 times. The coin landed on heads 12 times. What's the experimental probability? What's the theoretical probability? Well, remember, experimental is where you look at the experiment. So you do some stuff, you collect data, and that's what you're looking at. So the data we collected, I flipped the coin 20 times, it was heads 12 times. So 12 out of 20, experimental probability, which is 60%, sorry, I need it, which is 3 over, which is 60%. What's the theoretical probability of flipping heads? Well, now the theoretical probability, we do not look at the experiment. We forget about the experiment. We just look at the coin. So if you just look at the coin, just like before, there is one side that's heads, that's what we want, over the 2 sides total, which is 0.5 or 50%. We did not look at the experiment, at the data at all. And that theoretically, like when people are like, well, how are you going to win this next game? It's like, well, theoretically, we'll just do way better than them until we'll win. Well, theoretically, all this stuff will happen. Well, it's a theoretical, it's a theory because it hasn't quite happened yet, so you're guessing. Looking at the information you have. So theoretical probability, again, it has not happened yet. You're just forming a theory. You're forming a hypothesis. But like I said, we're this one, and I haven't decided if I think on the quiz I said 2 points, 1 point each. But this is one that it's not really that bad. The math shouldn't be hard, but it's making sure you know the difference between those two options. I'll talk a little bit more about that once we're done with the second one. So the next one, again, I rolled this 4 times and twice. Now, again, don't get confused, and this is why, I kind of have to do it because I want to make sure you know these probabilities, but it's hard for me to use a dice for options because a lot of people see the 3, and that's what they think they're using. They put 3 over 4. No, it rolled a 3 twice, so it's 2 times it rolled a 3. So what's the probability that I rolled a 3? Well, it is 2 out of the 4 times you did it. 2, which is 0.5, which is 50%. We ran an experiment. We rolled that dice 4 times. It landed on 3, 2 out of those 4 times. The experimental probability is, that's funny, I didn't change that one. Sorry, this should say, or one of them should say, I guess you can pick which one. This should be theoretical. Make sure I change that for later. What is the theoretical probability? Well, again, now we're looking. The dice has 6 sides. One of them is a 3, so 1 out of 6. So that is 0.17 when you round, which is 17%. Now, just because I find it interesting, and I can force you guys to at least act like you're paying attention, it's interesting with this because one trial, one probability said you have a 50% chance of rolling a 3, and the other one said a 17% chance. That's a huge difference. So why is that different, and which one is more accurate? The problem is we only rolled that dice 4 times. So you guys, it's maybe easier thinking about a coin. If you flipped a coin and it was heads, and then you flipped a coin again and got heads again, you wouldn't just say, okay, well, it's 100%, I get heads. But that would be experimental probability. You got heads 2 out of 2 times, so the experimental probability is 100%. But that's what I was talking about earlier, where you have to do more than just a couple different rounds or a couple different chances. If you do this, and I should see if I can find a simulation, because you can do it on the computer where it automatically rolls virtual dice, and it does 10,000 of them really fast. The more you do these, the more they're going to end up being the same number. So again, if you do this 3 times, it's not very effective. If you do it 10 times, it's not very effective. If you do it 50 times, it's going to get closer. That 50% is going to get closer to 17. If you do it 1,000,000 times, it's going to be very, very close. So which one's more accurate? It just kind of depends on how many times you run the experiment. And there's all these other variables where every dice that they make is supposed to be fair, but if it's weighted a little bit or if it's worn a little bit differently, so maybe the experimental is more accurate because you actually are using that specific dice and not a theoretical dice. But it kind of all depends. The punchline I want you to walk away from with this little speech at the end, make sure anytime you ever look at a survey or a probability or anything, it completely depends on how many students you do, and the more, or sorry, not students necessarily, people or more trials, the more you do, the more accurate it is. If you do 10 of them, that's great. If you do 10 million, it's way more accurate. So that's one of those things that you don't use a lot of Algebra 2 in life, but next time you hear a probability or a survey, you should ask yourself how many people that they actually surveyed. Okay, obviously there is a worksheet, there is an exit ticket, so make sure you're working on those. Again, tomorrow you're doing a quiz probably, and then you'll have a quiz on Friday.